discoveries 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hello everyone and good evening. Thanks a lot to ASRG for giving us the opportunity to host this presentation this evening. Let me introduce our topic. This is about the safety, integrity, and or versus cybersecurity assurance levels. I have to warn a bit up front that the presentation will overlap quite a lot with the functional safety area. So actually the first third or even close to half of the presentation will be about safety and functional safety and about the lessons learned taken in there to be taken over into cybersecurity area. I hope, given the fact that there will be a lot of talk about standards, norms, and regulations, I hope that won't be a boring topic. I can assure you that I'll give you my best to make it as exciting as possible. Before starting, let me say a couple of words about my company, clockworkX. So we are a relatively small company with around 15 employees, founded and located near Munich, relatively young company, so 4 years old. We are basically providing consultancy activities into two types of areas. So what we internally call 3S, safe and secure systems, and PRO, predictable and reliable operations. We are supporting the projects in different types of industries, so ranging from automotive, railway, machineries, and all types of activities. So from different types of analysis, engineering processes, implementation, design implementation, test and validation consultancy for different types of stakeholders. So for OEMs, for Tier 1, or for Tier 2. We're also having a quite close collaboration with academic and research milieu, especially with the Technical University of Munich, from Munich. Good, let me continue with myself. I took over the role of head of cybersecurity at clockworkX for about 1 year ago. Before that, my background was focused on functional safety area. That's why, as I said at the beginning of the presentation, there will be a lot of focus on functional safety on this evening's presentation. So I've been dealing in the last couple of years mainly with functional safety standards, so from different industries, so starting from the general, the so-called mother safety standard IEC 61508, through automotive, through machinery, railways, so supporting in different ways, so from coaching and the training, the customers, also in providing consultancy expertise for audits and assessments, also being myself a member of automotive software consortium called AutoSAR, so the Functional Safety Working Group for that. And since about 1 year, so we started to roll out cybersecurity projects and doing basically similar activities or similar types of activities as in functional safety related to ISMS and organizational information and cybersecurity. Lately also related to CSMS or to the newly published automotive cybersecurity standards, so the ISO 21434, and also supporting and even performing by ourselves TISAX audits or preparing for such audits. Please allow me to quickly walk you through the agenda or the content of the presentation this evening. So first we are going to start with the reason of being for those integrity or assurance levels, basically that they express the different or the various engineering processes in between the completely unsafe product and a perfectly safe or secure product, which basically no one can guarantee. We are going to discuss on how those integrity levels are being applied in a state of the art and a really mature standard in functional safety in automotive. And namely the ISO 26262 standard, with a quick deep dive on how those ASILs, so automotive safety integrity levels, are determined, with the pros and cons of them, and with the whole criticism surrounding them so far. Then I'm going to slowly transition into the security area, starting with information security. So starting with the first standards published by around end of 70s by the Department of Defense in United States, prescribing such assurance levels. Then we are going to say a couple of words about the internationalization and the overall standardization of this approach in the next standard for assurance levels called Common Criteria, which became an ISO and also an IECE standard. And then say a couple of overall remarks about the key features that are to be taken into account in information security as well as in cybersecurity, namely the CIA triad, so confidentiality, integrity, and availability properties. Based on them being structured all of the integrity and assurance levels. Then I'm going to continue with the cybersecurity sibling standard of for automotive functional safety, namely ISO 21434, with a risk approach in there and with the recommended CAL levels in there, cybersecurity assurance levels. What is their purpose? What is their meaning? Compares and contrasts with the ASILs that we previously spoke about in functional safety. Concluding in the end with some overall remarks in general, compare about how risk can be associated with such integrity, respectively assurance levels in cybersecurity as well as in safety, and then finally having some concluding remarks. So why do we have levels? Why do we have in general integrity or assurance levels, and what is their meaning? They basically are used as a tool in between different stakeholders, in between different tires, to have a common reference of what types of process methods have to be implemented in a certain product based on different types of risks that product can generate. So this is why they basically fill in the gap in between a perfectly safe or secure product and a completely unsafe or unsecure product. So, as said, they could be taken as a risk modeling tool to transmit in between the stakeholders what type of methods and processes then basically are applied to corresponding products. So we are going to see later on in this presentation when some stakeholders is talking about an ASIL B, for instance, product, then this is basically a common reference to the whole automotive industry, is that all of the tires, including OEMs, they know what type of design and verification processes, what type of testing has been put into that product, how does that product look like in regards to its design. This is the main purpose of the integrity or assurance levels. So to transmit a minimum set of common requirements that have to be fulfilled within an industry, within different stakeholders. There are, of course, drawbacks to it because there are different standards in different types of industries, defining on their own those levels which mostly they do not match to each other. So it may occur to be that they are not so well harmonized. It may occur to be that for some product supplier that they might not be so easy to communicate the same type of integrity level from one industry to, say, from automotive into another, into let's say machinery industry. So that could be different. In automotive industry, this process of linking certain risk associated with a certain type of car function or a car system was becoming quite mature and quite state-of-the-art, as well as standardizing those ASILs. So it's quite known across the industry for all of the tires, for the car manufacturer, for the ECU suppliers. When somebody is referring to an ASIL B or an ASIL C or an ASIL D type of function or type of product. Let's have a quick deep dive on how do we come to those ASILs, how are they prescribed by the ISO 26262, concluding this section related to functional safety with some remarks and some criticism linked to those ASILs. In automotive functional safety, but I would say in functional safety in general, the approach is to reduce the residual risk to an acceptable level. And this is actually what the ASIL of a certain product or a certain system reflects. So let's take simply a car steering system, which usually we are going to see it later on when we see how this ASIL is determined, that the steering systems are considered the highest critical systems in a car, for instance. Then there is to say that the higher the risk the steering system is exposed to, the more engineering effort has to be invested into that, and then the more basically it has to be fought with the complexity associated with that system implementing the steering function. The ISO 26262 standard, we have to say it's a pretty wide and complex standards, so all in total about 12 volumes, each of them around 100 pages, roughly half of them normative sections, the other half informative sections, annexes, roughly 130 documents or work products required by the standard, 800 or around 800 requirements to be complied with. As mentioned, a mature state-of-the-art standard published more than 10 years ago. It's now at the second edition, incorporating more and more semi-autonomous driving functions. When talking about functional safety in automotive and in general, we have to keep in mind that there is actually no 100% sure guarantee of a perfectly safe, or as we are going to see, of a perfectly secure system. That's why the levels are coming into the play. But back to the determination of the ASIL. So here we have those letters which basically correspond to the ASIL levels that we've been discussed. So ranging from A to D, so with the A being the lowest or the one associated with the lowest risk, D being associated with the highest risk. And those ASILs are determined based on three parameters. The one is the severity, which is the impact on the driver or on the traffic participants in case of system failure. Exposure, or different levels of exposures mentioned here, those are basically the driving scenarios that where that system may be used, and implicitly when a failure of that system can occur. And controllability, the C's here, is basically the driver possibility to avoid the risk once system failure already occurred. The QM here, so the green boxes, then basically they are out of the standard. So once this ASIL is determined as being a QM, that is to say the procedures would be outside of the standards. Basically, that product or the function associated with that product can be or is allowed to be developed outside of ISO 26262, so that it doesn't apply. It can be applied any quality management standard as it is in automotive, so the ISO 16949. At a very rough overview, at a bird's eye view of the standard, we may conclude that the four ASILs from A to D then are structured on three types of pillars or three types of requirements. So one of them is in regards to the type of management effort has to be put in. So the higher the ASIL, the more the independence level of verification or of review of certain documents, work products, associated with that system, and obviously additional number of activities to be performed, as for instance additional types of analysis, as we are going to roughly seeing, for instance higher ASIL systems that would require additionally in fault tree analysis, additionally to an FMEA. The second one would be in regards to the engineering processes related to it. So the higher the criticality, the higher the ASIL level, then let's say the harsher the design and development measures are compelling or are highly recommended. The more types of testing or test methods are required. And the third pillar of the ASIL is basically the product design itself. And this is quite a lot bound to the hardware failure rates and to the reliability of a project, of a product, pardon me. So for instance, for higher ASIL systems, there are required obviously lower failure rates and overall better design, better hardware design to support that higher ASIL functions. At the very first glance, if we were to name a couple of key features that would make each of these safety integrity level distinguishable from the other ones, would be those ones. So as you would remark in here, the ASIL A key features would not be probably too far away or too much overhead on a QMS standard. For an ASIL B, there's a bit more of requirements to be considered. For an ASIL C, even a bit more. And for an ASIL D, there are the most stringent hardware integrity requirements, namely hardware failure rates, as well as very deep, very good coverage of the software. That is to say, and the modified condition decision coverage metrics, they have to be applied and they have to be close to 100%. That is to say, close to 100% of function and branch calling software. Here is also a very rough overview of the tables, the famous tables prescribed by ISO 26262, with the key differences on a certain pickup elements out of the V development model, and where and how exactly do they differ from one ASIL to another. So you can roughly see how exactly is the standard more compelling for verification methods, or software structural coverage, as discussed previously. What type of additional safety activities, implicitly what type of safety analysis are being differently applied for higher ASILs than for lowers, and also an indication about concrete reliability failure rates to be applied for different ASILs. Okay, now that we had a quite deep dive into functional safety approach to the levels, let's transition now to the cybersecurity and let's see how was this approached in the past, how could it be approached in the present, and what recommendations or where can we head to. So we are going to start with a rough overview with one of the first standards to do recommendations and prescriptions on different information security levels, which is a military standard published by the American Department of Defense called TCSEC. So end of the 70s, beginning of the 80s. This is the so-called Orange Book. And then we are going to discuss about the internationalization of this approach within the common criteria, of course, with a step in between an European correspondent of this Orange Book, which I'm not going to mention explicitly. But we are going to head towards the ISO/IEC common criteria standard and to have a rough overview of the EALs in there, so the evaluation assurance levels. And then we are going to conclude this part with some remarks about the key safety cybersecurity features, namely confidentiality, integrity, and availability. Okay, so given the fact that this is actually a military standard, the TCSEC, so the so-called Orange Book, published as said end of 70s, the focus is on confidentiality. So this is basically with the purpose that every service supplier that they know or they have a common reference for the software products to be delivered to Department of Defense. That is to say, so the higher the criticality of this software, of information, of IT software product, then the more granular or the more refined the access control types have to be, the more refined have to be the security levels for the corresponding software entities, the more refined it have to be also the types of authentication. Also, every path or every communication path in between the trusted software system and the user has to be guaranteed. And then last but not least, there are the management requirements, as we also saw in functional safety. So the more constringent are those assurance requirements in regards to the configuration management. So there is to say, the more types of or the deeper granularity of the items that has to be associated with certain testing or development activities has to be documented and audited. The more robust the architecture has to be, the higher the assurance level is, and of course the more robust the type of testing has to be performed. During the years, there was a growing consensus in harmonizing this initial approach of American DoD, and then in the end, basically a need for international standardization of this approach. That's why the common criteria ISO standards come into existence, prescribing similar number of assurance levels that we are going to see them right away. There was nevertheless associated with afterwards criticism in regards to that, as we're also going to see in regards to automotive cybersecurity assurance levels. Criticism backed basically by the fact that such standards or adherence to such approach would be rather focused on the process, and the investment would be rather on the process than on the product, and basically that would not make the product itself more secure in itself. There was also the aspect that less industry input has been considered in common criteria, as probably in the automotive cybersecurity standard that we are going to talk about right away. So common criteria prescribes the so-called EALs, evaluation assurance levels, ranging from 1 to 7. We can notice that the basic approach here is first to start or to prescribe more stringent methods for testing. And then the higher the EALs, and basically the stringency is required for design. So we can notice that more or less starting from EL4, the design is required to be semi-formally or first methodically defined, and then start continuing with EL5, so to be semi-formally specified. So let us have some few concluding remarks about this quick historical overview of the standard. So we started with some military standard focused on confidentiality. Then we saw when this became internationalized, when this became ISO or IC standard, then the more integrity features have been incorporated. That is to say, so in order to conclude, and this is basically the two aspects, confidentiality and integrity, along with the availability, they are the key pillars to that the whole cybersecurity is structured to, and all of the engineering activities are based on. This have been extended with the so-called security hex set, so with additional 3 ones mentioned here, and those are basically parallel to the safety ones that we discussed previously, namely integrity and reliability. Let us now take a look at ISO 21434, so basically the first technical cybersecurity standard for automotive. Let us roughly see the approach towards cybersecurity risk in there, and also the recommendations in regards to cybersecurity assurance levels. And let us conclude then this section of it with short comparing between the different ASIL types in automotive and the recommended CAL levels in here. So this is a brand new standard, recently published. As a matter of fact, the first official version has been released this year. Was coming out of general international consensus of the automotive industry to have this basic standard. Is basically a process-oriented standard rather than a product-oriented standard. Is not as technical and not as wide as we saw the ISO 26262. So when it comes to the number of requirements, when it comes to the number of work products required or of the activities, and it is also based on the V model, since the V model is state-of-the-art development in automotive industry. One of the key aspects that this standard stresses on, and also one of the benefits for the overall understanding in the industry of the risk, is that the differences that the standard emphasizes between the cybersecurity risk and certain assurance levels. Due to the nature that cybersecurity, due to the unpredictability of the cybersecurity risk, the fact that is far more dynamic than in safety, far more or far harder to be approximated, it's also harder to bind or to link corresponding assurance levels, or as we saw, integrity levels in functional safety to cybersecurity risk. The standard recommends, and here with a stress on the word recommend, the so-called assurance levels, the so-called CALs. So those are part of the annexes of the standards, so are not normative, are not compelling, along with the whole procedure on how those CALs can be determined. So this is in a more or less similar manner as for the functional safety ASILs. This is based on the impact, as we saw previously, the severity or the functional safety standard. So this is associated with the cybersecurity attack impact on the considered car functions, and the attack vector. The different call types, they are associated with different types of engineering methods. We are going to see right away that those are rather with a focus on verification, so that is to say on testing, and they are not bound so far in any manner to some technical requirements. Yeah. If we were to scan those calls, so from the lowest critical one to the highest, those would be basically the key differences in between different calls. So here on the left-hand side, there are the key characteristics and the philosophies behind the engineering methods for call 1 and call 2, and here on the right hand side, so basically the ones for call 3 and 4. So let us please have a comparative view of the engineering methods prescribed by the one standard, so by the functional safety automotive. So here on the left side, and by the cybersecurity by the ISO 21434. So we can notice that the methods and the approach in cybersecurity here is almost similar to the one in functional safety. So as said, the focus in cybersecurity, or the engineering methods for the call levels, their focus is rather on the verification methods. So all of them, they are more or less verification, so test or analysis methods, but their counterparts in functional safety, they look quite similar. So there's almost one-to-one match in between different ASIL levels in automotive to the calls in cybersecurity. In order to wrap up and also to conclude this part of the engineering processes related to the cybersecurity assurance levels, let me express a bit of criticism or some, let's call them gaps that I see to them, given my experience in functional safety with siblings ASILs. So as you probably have noticed, there's no emphasis at all on any different types of hardware secure architectures for different types of calls. So no reference to different types of hardware secure modules as they are specified in standards like EVITA or like that. No differences, no different emphasis on after production requirements based on call levels, although we just saw previously that after production activities, they may be key to cybersecurity. Also, the attack feasibility parameters, so aspects like knowledge of attacker knowledge of the item, or attack window of opportunity, or attack equipment required. It's not included in the call determination as it is recommended standard, and also no emphasis on any different type of encryption algorithm or authentication methods depending on different call levels. Before concluding, so let me do some cross remarks between functional safety and cybersecurity. So as I mentioned many more times, there are a lot of lessons learned to be taken over from functional safety. More mature area within the industry with a more mature and older standard, which is ISO 26262. It looks to be that the direction in which the ISO 21434 is going is to be along the same line as in functional safety. So as we saw, most of the management activities, they are basically equivalent in the cybersecurity standard as in safety. So that is to say, the premises for this cybersecurity standard would be that if good, robust quality management and also functional safety management is already established, then the shift or the overhead for cybersecurity, that should be minimal in regards to that. There are nevertheless some particular aspects that would be interesting to see how they will be considered in the future in cybersecurity, and this namely in regards to off-the-shelf products. If we were to remember the previous cybersecurity standards, so the Orange Book and the common criteria, that was their primary purposes to specify concrete requirements and buyer expectation from software vendors for different types of cybersecurity risks and the corresponding assurance levels assigned to them. So it would be interesting if this will also be valid for the current calls. Another aspect that it's interesting to follow, that would be the consideration of mixed environment, as said. So when CAL-related elements and non-CAL-related elements will be mixed up on the same item. So to say, in other words, that cybersecurity relevant components are allowed or are not allowed to be mixed up with non-cybersecurity related components. So this is very interesting topic in functional safety area, for instance. And also another aspect would be to see to which extent we will go towards some sort of pre-classified cybersecurity systems. So something similar to functional safety as we have it, for instance, that certain functions that are kind of already have the ASIL already determined. So as we mentioned, the steering is a kind of pre-established as being an ASIL-D system, longitudinal dynamics, so braking or acceleration functions, they might be somewhere around ASIL-C, exterior, interior lights, exterior lights especially, they are mainly considered as ASIL-B. So will we have something similar in cybersecurity? Will we have a kind of pre-classified system? So that is, it will be interesting to follow it in the industry. Okay, then let me conclude my presentation along all the remarks and the references I did all across the presentation, and also depicting the similarities and the differences between the two areas. I would say all in all that the direction towards automotive cybersecurity standardization is rather as a larger framework of standards and the normative references, instead of let's say more monolithic approach as in functional safety, where all of the requirements are more or less contained in one single standard. That being said, I thank you very much for your time and for your attention, and I hand it over back to our ASRG presenters. Thank you very much.